Dear students, it's very happy to see you once again and I welcome you to online classes D1 Algonda. In our previous class we have seen that when electric conductor is placed in a magnetic field is produced around the current carrying conductor. Okay. In this class we will see when the when the current carrying conductor is placed in a magnetic field, there will be two magnetic fields, because already we have seen that while the current is carrying in a conductor, that current carrying conductor behaves like a magnet. It means the magnetic field is produced around the conductor. Okay, already it is placed in the magnetic field, so that there is a impact of these two magnetic forces. Due to that, there will be a force applied on the current carrying conductor. Okay. To understand this, let us imagine one uniform magnetic field, that is B. Okay, this is a uniform magnetic field. Okay, one current carrying conductor. Consider, let us, this is B. One current carrying wire is passing through this magnetic field. I current passes through the conductor. Okay, the length of the magnetic field will be capital L. We know the formula, that force applied on the current carrying conductor due to this magnetic field, F is equals to Q VB. Okay, actually we know that the current means it's a moving charge. Okay, so that the force applied on each charge, if we consider that is F naught, then this will be Q naught, V and B. Here Q naught is the charge, V is the velocity of the charge and B is the magnetic field. Okay. For example, if the force applied F naught is on the single charge, the net force applied on the complete charge which is passing through the conductor, let us consider that is F, that will be Q, capital Q, V and B. Okay, here this will be the net charge, this is the velocity and this will be the magnetic field. Okay, now we will find out the velocity of the charge. We know the formula of velocity is distance travelled by time. It means here the distance will be the length of the magnetic field, capital L, and the time is small t. If we substitute V is equal to L by T value in this above formula, then F can be written as Q L by T and this will be B. Okay, now this can be written as Q by T, L and B. Q by T we know that will be the current, so this can be written as I L B. This can also replaced as B I L. It is very easy to remember if we write this formula as B I L. F is equals to B I L. BIL means it's a bill. By that way we can memorize this formula very easily. Okay. Now we will, for example, this electric current is passing in the same direction of the magnetic field. It means the both are in the same direction. If the both are in the same direction, we will not find any force applied on the current carrying conductor, because we know F is equals to Q V B sin theta. If both are in the same direction, it means the electric current as well as the magnetic field are in the same direction, then theta will be 0, then sin theta will be 0, then net force will be 0. It means the current carries in the same direction, the direction in which the magnetic field, so the net force applied on the current carrying conductor will be 0. Okay. Next, if there will be, for example, here you observe this figure, the magnetic field and the current carrying conductor, both are perpendicular to each other. Otherwise, they are making some angle with each other. In that special condition, we can use this formula as F is equals to B F is equal to I L B sin theta. By using this formula, we can find out the net force applied on the current carrying conductor when it is placed on the magnetic field. Okay. By using this formula, we can find the net force. Okay. Now we will try to understand that if the force is applied on the current carrying conductor, what would be the consequences? Okay. To understand this, let us take two wooden sticks. They are having some slits at the one of their ends. Okay. This is a copper wire, passes through the slits and is connected to a battery as well as a switch. Okay. When the switch is on, electric current passes through this conductor. Okay. When the electric conductor is carrying the current, there will be a magnetic field around it. By using the right hand rule, we can find out the direction of the magnetic field. If this will be this is the direction of the electric current, and the curling finger shows the production of the magnetic field around the conductor. Okay. And now you place this horseshoe magnet. It is having north and south poles. Okay. The magnetic field lines travels from north to south. It means the current carrying conductor is placed in a magnetic field. Okay. Already, as this is a horseshoe magnet, there will be a magnetic field in between the ends of the poles, north and south poles. As the current carrying conductor is placed between these two poles, there will be a clash between the two magnetic fields. Let us try to understand what is the consequence or what is the result as the current carrying conductor is producing the magnetic field as well as when it is placed in the uniform magnetic field. Okay. Let us consider the magnetic field produced by the horseshoe magnet will be the uniform magnetic field like this. These are the magnetic field lines, imaginary magnetic field lines, but it is uniform magnetic field. Now the magnetic field produced by the current carrying wire, like this is into the, let us consider into the plane of the paper. Okay. Into the plane of the paper, for this will be the anti-clockwise direction. The magnetic field will be produced in anti-clockwise direction. See, as the uniform magnetic field travels towards this current carrying conductor, see, imagine that these lines are passing in this way, and the magnetic field produced by the current carrying wire also produces the magnetic field. The direction of the magnetic field produced by the current carrying wire is opposite to the magnetic field lines which is produced by the horseshoe magnetic field. Okay. It means both the magnetic fields are opposite to each other. When it comes to the upper part, both the magnetic fields are opposite to one another. Okay. But when it comes to the lower part of this area, this is the direction of the magnetic field lines which are produced by the horseshoe magnet. Okay. And magnetic field produced by the current carrying conductor is in this direction, It means both are in the same direction. As the both are in the same direction, lower part of this current carrying wire is having the more number of magnetic field lines. It means the magnetic field at the lower part is stronger than the magnetic field which is produced at the higher part of the electric conductor. It means here it is magnetic field is very strong and here it is a magnetic field is very low. Due to this impact, here we can find more number of magnetic field lines and here we can find the less number of magnetic field. The result of these, the combination effect of these two can be drawn like this. For example, this is the current carrying conductor. It means the lower part, more magnetic field lines are there, but upper part there are very less number, there are very less in number. It means either sides of the electric conductor is having, one side is a strong magnetic field, the other side is a weaker magnetic field. Due to this reason, the current carrying conductor is forced to move the area which is having the less magnetic field lines. It means the net force from this side is applied on the electric carrying conductor to push the other side, which is in this direction, which is having the less number of magnetic field. Okay, it means now in the first instance, when the current carrying conductor is placed in the magnetic field, force is applied. That force is calculated in terms of F is equals to BIL. Okay, now this current carrying conductor is placed in the uniform magnetic field. Okay, the impact of all these issues led to the force applied by the magnetic field on the current carrying wire. Okay, now let us imagine if this straight wire or the current carrying wire is replaced with a coil. If it is replaced with a coil when it is placed in a magnetic field. Okay, now let us see clearly. If this current carrying conductor is replaced with a coil and which is placed in a uniform magnetic field. This is consider this is a uniform magnetic field, and this will be the coil. It means this conductor is replaced with this coil. Okay, now these are the A, B, C, D. These are the sides of the this coil. Okay, now the electric current is passing from A to B, B to C, C to D, as well as D to A. Okay, by using the right hand rule, we can find out the direction of the magnetic field which is produced when the current carrying conductor is traveling from A to B. Okay, we know that so far we have seen that when the current carrying conductor is placed in a uniform magnetic field, the force exerts on the conductor. Okay, due to this we can say that, for example, let us consider this will be the rectangular shaped carrying conductor. Okay, for example, this is the side AB, BC, CD, and this will be DA. As the current is traveling from A to B, definitely there will be a force applied on this side of the coil. The impact of the force applied on this side, according to right hand thumb rule, we can find out the direction of the magnetic force. It will be the upward direction. It will be the upward. It means the side AB pushes in the upward direction in this way. It means like this. AB is lifted in upward direction and CD side is moving in the downward direction. So we can see this, we can show the forces. This will be the magnetic force applied on this side of the coil, and this will be the force applied by the magnetic field on the current carrying conductor on the CD side. This will be the direction of the magnetic field. Okay. Next, actually this force and the net amount of this force and the magnitude of this force both are equal, and see here opposite in the directions. We know that when the equal amounts of forces applied on the same object, then the net force applied by the both forces will be the zero. It means the equal forces in opposite directions, they work on the same object, the net force will be zero. But in this case, though different forces, it means the same quantity of the forces, and they are applied in the opposite directions to each other, but there will be a motion in the current carrying conductor. How it is possible actually? We have seen according to the Newton's laws, there will be two forces applied opposite to each other and the quantity is the same, then the net force applied on the conductor will be 0. But here it is happening differently. It can be explained in the terms of the pair of forces and the turning forces. We can call them as the turning forces. In case of the turning forces, the one pair of the opposite forces applied on the same body, there will be a motion in the object. It means that can be understood with help of this opening the cap of the bottle. See, to open this bottle or to close this, to tighten the cap of this bottle, we will apply the amount of forces by using these two fingers. Okay, one force is applied by this thumb and another force is applied on the index finger. See here, the two forces applied, two forces are equal and opposite in the directions. Actually it has to be 0, but in case of this issue, the bottle is moving and it is opening. It means whenever the pair of forces applied on either sides of one object, there will be a motion on the body if you want to tighten the cap or loose the cap. So that kind of forces are applied on the either both the edges AB and CD of the coil. By that way the coil moves. We can find out the motion in the coil. Okay, and see here, the direction of the electric current will be A to B, and here B to C, C to D and D to A. What would happen if we do not change the direction of the electric current? Can you imagine and can you tell me, if here each side, in each instance we can change the direction of the electric current, what would happen if we cannot change the direction of the electric current? See, what happens is, if the direction of electric current is not changed, see, this is the AB side. Okay, the direction of the electric current from A to B. Okay, when it comes to this side, the direction changes from C to D. These are the opposite in the directions. If we cannot change the direction of the electric current, actually it has to move up. Due to the law of inertia, it changes like this and it comes back into the original position, but it cannot continue to rotate like this. Unless we can change the direction of the electric current, we will make the armature to rotate in a uniform magnetic field. This principle has led to invent the working of the electric motor. Okay, now we will see how the electric motor works and what kind of energy will be converted in the electric motor. Okay, now I will draw the simple diagram of the electric motor. See, to understand the working of electric motor, okay, to understand the working of electric motor, let us imagine a uniform magnetic field which is having the north pole and the south pole. One coil is placed inside the magnetic field. Okay, here the commutators C1 and C2, or we can call it as slip rings. These slip rings are connected to brushes B1 and B2. Okay, you understood? And this is connected to a battery. This is a simple diagram of electric motor, but we can see in the textbook that will be the three-dimensional diagram of the working of electric motor, but by using this figure we can understand the working of electric motor very easily. This is A, B, C and D. The direction of electric current will be A to B, B to C, C to D and D to A through this arrangement. Okay. Now when the battery is on, the current carries from A to B. Okay. In the half rotation, as the current travels from A to B, it starts rotating in a clockwise or anti-clockwise direction. Okay. As it is rotating like this, in its first half of the rotation, the AB comes to CD side and the CD comes to AD side, but the commutator C1 and C2 also rotates along with the sides of AB and CD. It means the AB side is connected to, along with the AB side is connected to the brush B1, and the CD side is connected to along with the C2 with the direction B1. It means in the half rotation the direction of electric current is changed. As the direction of electric current is changed, you know, as earlier I have seen, this is the AB and this is the CD. Okay. For the first half of the rotation it turns like this. Okay. It means it turns like this, and I will explain you once. Actually it rotates from here to 90 degrees. Due to the law of inertia, it continues its motion and comes to this place. Okay. When it comes to this AB edge comes to this side, the electric current again travels through this, and the magnetic field produced, and also it the force applied on the side of AB pulls towards the downward side. So that's why it rotates in this way. Again Newton's first law, it means the law of inertia activates and it comes to the initial position. If we cannot change the direction of the electric current at its the half of its rotation, and again it comes back, we cannot make the armature to rotate continuously, so that we have to change the direction of the electric current. Unless we change the direction of the electric current from the side AB, we cannot make the armature, we cannot make the coil to rotate continuously. Okay. So in this as we have seen, AB side along with the C1 armature comes to B2 side, and the CD side along with the C2 comes to B1 side, brush B1 side. It means the direction automatically changes. So by changing this direction, this coil rotates in the uniform magnetic field continuously. This is the simple working of electric motor. Okay. You might have understood very clearly. So in this electric motor, the electrical energy is converted into the mechanical energy, because by using the electrical current we will bring the water from the deeper level of the surface of the earth. It means the electrical energy is being converted into the mechanical energy. Okay. So by using this, by drawing this diagram, we can understand the working of electric motor very easily. Okay. Hope you have understood, and we will meet you again. We will meet in the next class with a new topic. Okay. Thank you.